Dear all, welcome back to our channel. Let's discuss very important spectroscopic technique, that is nuclear magnetic resonance spectroscopy. The nuclear magnetic resonance spectroscopy is generally represented as NMR. N stands for nuclear, M stands for magnetic, R stands for resonance. What is the main aim of this spectroscopic technique? The main aim is to identify the behavior of nucleus. So NMR spectroscopy explains the behavior of nucleus in a particular chemical system. In order to identify the behavior, we have a condition. What is that condition? Nucleus must be magnetic in nature, and that should be follows resonance. Magnetic condition must be present and resonance condition must be followed. If the nucleus follows these two conditions, then we can identify the behavior of that particular nucleus. So in generally we can say that we are going to know the behavior of nucleus by using NMR spectral technique. If you see NMR, we have different kinds. First one, Proton NMR, C13 NMR, Phosphorus 31 NMR, F19 NMR, B11 NMR, Deuterated NMR, N14 or N15 NMR. Among these different kinds of the NMR spectroscopic techniques, we are going to emphasize on main two techniques. Those are Proton NMR and C13 NMR. Okay, let's start the first one, proton magnetic resonance. We all know that the proton has three isotopes, 1H1, 1H2 and 1H3. Among these three isotopes, the naturally highly abundant isotope is 1H1, right? If you see the applications, by using the proton NMR technique, we are going to identify the nature of hydrogen atoms present in different kinds of the samples. We know that organic chemistry is the carbon chemistry. Carbon is the main element. Along with the carbon, number of hydrogens are there. So if you identify the behavior of hydrogen and carbon, certainly we are going to get some amount of information about the unknown chemical structure of any kind of organic compounds. That's why in this proton NMR, we are going to identify the behavior of different kinds of the hydrogen atoms which are attached to the carbon and different heteroatoms. In case of amines, we can observe NH bonds. In case of alcohols, we can observe OH bonds. It will deal with chemical equivalency and chemical non-equivalency of protons in a sample, and also nature of neighborhood protons for the selected reference protons, and will also give the geometrical relationship of the protons. We all know that we studied in stereochemistry cis trans isomers, ez isomers, exo-endo isomers. In those kind of compounds, we are having the protons with different relations, cis, Ez and exo-endo. Such kind of relations are going to be identified by using this proton NMR technique. Next, the influence in different kinds of the rings. Steric crowding we can generally say, or we can say ring strain. How we are going to identify and how these are going to affect can be studied in this particular technique. The first one and very important one is identification of chemical equivalency and non-equivalency set of protons. We have different kinds of organic molecules, right? In the different kinds of organic molecules, we are having different kinds of the protons attachment to other atoms. We can say sp3 hybridized carbon attached to proton, sp2 hybridized carbon attached to proton, sp carbon hybrid attached to proton can be observed, right? So initially we need to identify what are the chemically equivalent protons and what are the chemically non-equivalent protons. For that purpose, we are having three rules. First one, connectivity rule. substitution criteria, symmetry criteria, and stereochemical relationship of protons. Let's discuss one by one. Connectivity rule. This is very simple rule. See that one. For selected protons, if nature of chemical connectivity or chemical environment is same, then those protons are called chemically equivalent in nature. If that is not, chemically non-equivalent. See the simple example. We have CH4 molecule, right? In the CH4, we are having how many hydrogens? 4 hydrogens are not, H1, H2, H3, H4. All 4 hydrogens are connected to the single carbon or not. It means all protons are having the same connectivity, having the same chemical environment. That's why all these 4 protons are chemically equivalent. This can be considered as one set. If you have one set of protons, we will get one signal in the spectra. Similarly, take next molecule CH3. Here we have 6 hydrogens or not? But the number of carbons are how many? 2 are not. 6 protons are connected to 2 carbons. Now we need to identify both carbons are same or different. If you observe, the C1 and C2 both are sp3 hybridized carbons or not. So all 6 protons are attached to sp3 hybridized carbon only. So the chemical environment of all 6 protons are same. That's why all 6 protons are considered as one set. One set means it will give only one signal in the NMR spectra. Take the next example. In the next example, see this, we have 6 plus 2, 8 protons, right? If you see this part, this is CH3, this part, this is also CH3. These two carbons are primary carbons or not? So the protons attached to the primary carbons will have the same environment or not? That's why all these 6 protons are considered to be one set. See these two protons, Hb protons, these two are connected to different carbon or not, secondary carbon or not. So the protons attached to the secondary carbon, their environment is different. That's why all 6 protons are considered as one category. The remaining 2 protons are considered as another category. It means in this molecule we are observing 2 sets of protons. That's why in the spectra we will observe 2 different peaks. I think I am clear in this particular part. Similarly, see the next molecule. In the next molecule, what we are observing? 2 primary carbons. That's why primary carbon attached protons are considered as one set. See these 2 carbons. These 2 are secondary in nature or not? That's why all these 4 protons connected to these 2 carbons are considered as one category. So totally we are having 2 sets of protons, means we will get 2 peaks in the spectra. If you see this molecule, the central carbon atom connected to 4 CH3 groups. All CH3 in which carbon is primary or not? That's why all protons are considered as one set. So in this way we can identify the environment of different kinds of the protons which are attached to the different atoms. Suppose if you take this molecule ethyl chloride. In this case what happens? The carbon chain is connected to chlorine atom, halogen atom. Here we are observing the inductive effect or not? More inductive effect is observed on the first carbon, then followed by second carbon. It means the environment around both the carbons are different or not? So environment around the both carbons are different means the hydrogens which are attached to those carbons, their environment is also going to be different or not? That's why in this particular molecule, first 2 protons will considered as one set, next 3 protons will considered as another set. That's why in the spectra we are going to observe two different peaks. That is two non-equivalent sets of proton. In the first set, two protons are there. Those are having same environment. In the second set, we are having three protons. Those are having the same environment. See the next example in which what we are observing. CH2 attached to what? Same chlorine or not? That's why all protons are one set. But in this case, one side we have bromine, another side we have chlorine. It means both carbons are having different environment or not. That's why the protons attached to those carbons are obviously chemically non-equivalent. So we observe two sets. That's why two signals. Take the next molecule. See this one, we have two carbons. One carbon is connected to one proton. Second carbon is connected to three protons. Okay, but at this carbon we are having two bromine atoms or not? Direct influence of bromine atoms on the first carbon. That's why the environment of first and second carbons both are different. So ultimately these protons are going to be non-equivalent. That's why we are observing two sets. In this case, chlorine attached to center carbon. That's why the protons on these two CH3 groups are same and the middle carbon is different, two set. Similarly, in the next example, neopentyl chloride. This is a kind of set. Remaining all groups are same or not? Same environment. That's why observing two sets. So in this way, we can observe different kinds of environments of the protons which are attached to the different carbons. If you take cyclic compounds, take this cyclopropane, CH2, 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 CH2. So 6 protons we have, all 6 are having same environment or not? That's why one set. In case of cyclobutane, cyclopentane, cyclohexane, cyclooctane, heptane. So in all these cases, we are going to observe a single peak. Okay. Now we have some more examples. See this one. Here we have a molecule. The functional group is COOH. Simply and blindly remember one thing. Whenever we have a lengthy carbon chain, at the end of the lengthy carbon chain, if you have some any electron releasing group or any electron withdrawing group, automatically all the carbons which are connected to that particular group are going to be chemically non-equivalent because of the minus psi effect and plus psi effect. In this case, what we are observing, electron withdrawing effect, that is minus psi effect. That's why all protons are chemically non-equivalent. That's why we will observe different kinds of sets. But in the functional group, see this one, hydrogen attached to oxygen or not? Here protons are attached to carbon. That's why this environment is different or not? That's why this will be considered as one another set. Okay. Similarly, CH3 and H2. These two protons are having different environment. These three protons are having different environment. So two sets. In case of methanol, this is one set. This is another set. Acetic acid. Similarly, in this way, we can identify different sets of protons. These are some of the examples. Okay. Now let's see how can we identify the nature or connectivity of hydrogen atoms in the aromatic system. In case of aromatic system, the first one is what? Benzene or not? Benzene molecule having 6 protons. All 6 protons environment is same or not? That's why that will be considered as one set. So we will observe only one signal. In case of alkenes and alkynes also, only one set. So we have different kinds of substitutions in aromatic compounds or not? Mono substitution, di substitution, tri substitution. We are having different substitutions or not? So let's see the first one, mono substituted benzene. If we have the mono substituted benzene, we have three different positions or not? Ortho position, para position, meta position. the influence of this substituent is different on ortho, para and meta or not. That's why what happens, the environment of those carbons are obviously different. So protons attached to those carbons are different. That's why all orthoprotons will be considered as one set of protons, all metaprotons will be considered as one set, and paraproton will considered as one set. That's why in this case we observed three sets of protons. Three sets will give three different signals. Okay, let's see some of the examples. First one, phenol. In phenol, ortho position one set, meta one set, para one set. Three different sets. Along with that one, here we have OH group or not. Here oxygen is connected to hydrogen. Na? It means the hydrogen environment is different or not, comparing with the hydrogens connected to the benzene ring. That's why it will be considered as another set. This is D. So we are having four sets of protons. Four sets of protons will be giving four different signals. Similarly, benzaldehyde, three with ortho parameta, one with aldehyde. In case of benzyl alcohol, three with ortho meta para, one with benzyl, another with OH. Five sets of protons. So in this way you can identify the mono substitution. Now come to the di substitution. In case of the di substitution, we are having three different kinds of substituents. Ortho di substitutions, it means the substitutions are ortho to each other. Meta di substitution and para di substitution. If you see this kind of di substitution, here the X is same or not. Okay, suppose if you assume that the X is Cl. So 1 comma 2 dichlorobenzene, 1 comma 3 dichlorobenzene, 1 comma 4 dichlorobenzene. So in such type of cases, how many sets of protons are identified? See this? With respect to these two groups, these two protons are having same environment. Why? Because X group is same. With respect to X, both are ortho. Right? The influence of X group is same on both the proton. That's why it will be considered as one set. These two will be considered as another set. But in case of meta substitution, what happens? See this one. This proton and this proton having the same influence. This one having different influence. This proton is having different influence. That's why we're having three sets of protons. If you take para di substitution, if you observe this one, here we are observing plane of symmetry or not. See this? In this way we are observing plane of symmetry. So these two protons are same, these two protons are same. Suppose if you take plane in this way, these two protons are same, these two protons are same. That's why we will observe only once all protons are chemically equivalent in nature. See the examples. You can use some general example, like if you take chloro, dichloro, dibromo. Okay. Suppose if X and Y are different, obviously what happens? This proton is influenced by X, this proton is influenced by Y. That's why these two are chemically non-equivalent. If these two are non-equivalent, automatically the influence on the remaining protons are also different or not. That's why we will observe four signals. Here also similar kind. The H is in between X and Y. That's why different environment. X is influences the HC, Y influences the HB. That's why these two are different. Again this one will be different. Four sets of protons. In this case, the X influences these two equally. In case Y, the Y influences these two differently. That's why these two will be considered as one set and these two will be considered as another set. So Two sets we will observe. Similarly, we are having that tri-substitution. Similar kind. These three groups may be same, these three groups may be different. If these three are same, two sets. If this kind of substitution, three sets. This kind of substitution, one set. If two are same and one is different, three set, three set, three set. This is very simple. Need not to explain each and every one. The concept is same. Connectivity rule. Connectivity means what? Where the hydrogen is connected. That connectivity is having the same environment or not. If you observe same environment, that is called chemically equivalent. If you will not observe the same environment, that is chemically non-equivalent. So in this way we can observe different sets of protons by using the connectivity rule. Okay, so in most of the cases we will follow connectivity rule only. Other than the connectivity rule, we are having some more rules. Let's see those also, but give the preference to connectivity rule only. Substitution criteria, the name itself indicates substitute. Whatever the hydrogen whose environment is going to be identified can be substituted by some another group. Take the first molecule, C. CH4 methane we have. In the methane we have 4 hydrogen atoms or not. Now we need to prove all the hydrogen atoms are same. So how can we prove? By using the substitution. According to connectivity rule, are all connected to the same carbon, that's why all are same. But according to substitution, see this one. Suppose if H1 is replaced with Cl, what can we get? Methyl chloride or not? H2 is replaced with Cl, what you will get? Same methyl chloride. H3 is substituted with Cl, same methyl chloride. H4 is substituted with Cl, same methyl chloride or not? So what we are observing? By changing the selected proton with the third different atom or group, if you will get the same product in all the cases, then we can say that all the protons are chemically equivalent. See, in all the cases we are observing methyl chloride or not. That's why after the substitution of each hydrogen, we are getting the same product. That's why all 4 protons are chemically equivalent in nature. Suppose if you take second molecule CH3, CH3. Here also we will observe one chloroethane only. Substitute all protons with chlorine. You will come up with one chloroethane. But if you come to this one propane, suppose if these hydrogens are replaced by Cl, you will get what? One chloropropane, one chloropropane. But if the middle hydrogen will be changed with the chlorine, what we are observing? Two chloropropane or not? Right? I think you understand very well. By the replacement of the selected proton produces the different product, then we can say that is chemically non-equivalent. If it produces same proton, that is chemically equal. So in case of 1 and 3, we are getting the same structure, one chloropropane. That's why these 3 proton and these 3 protons are chemically equivalent, only one set. But if you replace these 2 protons with the chlorine, you will come up with 2 chloropropane. Remember one thing, we cannot directly replace any hydrogen with chlorine or any other atom like this. Substitution criteria is a hypothetical method for the determination of the different kinds of the protons. Okay, don't think that we can simply remove hydrogen and attach chlorine. It's not possible. Okay. So these are some more examples related to the substitution criteria. Here see this. We have a phenol, right? According to connectivity, ortho same environment, meta same environment, para same environment. That's why ortho considered as one set, meta considered as one set, and para considered as one set. According to substitution, if HA is replaced with Cl, you will come up with what? Orthochlorophenol. Hb is replaced with Cl, metachlorophenol. Hc is replaced with Cl, parachlorophenol. So by the replacement of these protons with chlorine, giving different products or not. That's why Ha, Hb, Hc are different in nature. Three sets. Okay. Similarly, you can identify the protons by using the substitution criteria. Now come to the next criteria, that is what? Symmetry criteria. In stereochemistry, we have identified different kinds of protons: homotopic protons, heterotopic protons, in which enantiotropic protons, diastereotropic protons we have studied. Homotopic means same environment. Enantiotropic, diastereotropic means different environment. So homotopic means chemically equivalent. Heterotropic means chemically non-equivalent. Very simple. Okay. See this. These protons are homotopic in nature, that's why equivalent. These protons are enantiotopic. See this one. Enantiotopic means heterotopic. So chemically, here one point we need to understand. In case of the enantiotopic protons, if you use a non-polar solvent, then it will be considered as chemically equivalent. If you use some polar solvent, these will be considered as non-equivalent. We can say in terms of stereochemistry, a chiral medium and chiral medium. Homotopic protons are always chemically equivalent. That is the standard line. Second one, in case of enantiotopic, if you use the achiral medium, the protons are chemically equivalent. If you use the chiral medium, the protons are chemically non-equivalent. In case of diastereotopic, the protons are always different, non-equivalent. These kinds of examples are very, very, very important. Suppose if the X is replaced by benzene, what happens? We will get styrene or not? In most of the cases, people will ask you, in styrene, how many sets of protons you will observe? Assume that if the X is benzene, benzene means ortho, meta, para. Three sets are there. In case of benzene, this is one set and these two will be considered as some another set. Why? Because of the X, these two are acting as diastereotropic in protons. That's why these two are chemically non-equivalent in nature. Most of the cases, students will do the mistake. These two will consider as one point. Don't consider if X is some another atom, heteroatom or phenyl ring. Okay, if X is a Cl, OH, then it should be considered as diastereotropic in nature. If you see this one, with respect to Hc, this is cis in nature. With respect to Hc, this is trans in nature. Cis environment is different, trans environment is different. So environment different means what? Chemically non-equivalent. That's why the Ha and Hb will be considered as chemically non-equivalent. Here see this. These two are diastereotropic in nature. Diastereotropic means chemically non-equivalent in nature. See this one. With respect to X also we can say cis and trans. That's why chemically non-equivalent. If you use the substitution criteria, if the H is replaced with Y, here you are getting cis product, here you are getting trans product. So always the general condition is what? Cis trans protons and Ez protons are always chemically non-equivalent in nature. Similarly, with respect to this pi bond, this is syn in nature, this is anti in nature. So syn and anti-protons are always non-equivalent in nature. In non-Bornstein systems, we can observe the exo and endo. H is replaced with OH, you will come up with exo alcohol, endo alcohol. Nature is different. That's why exo and endo protons are always considered as chemically non-equivalent. Axial and equatorial protons are always considered as chemically non-equivalent. Remember, here we should have a substitution. Then only these will become non-equivalent. Otherwise, we can use some different conditions. Lower temperature, higher temperature. Dynamic NMR spectra. There we will discuss why the why the axial and equatorial protons are chemically non-equivalent. When it is chemically equivalent, when it is chemically non-equivalent, we will cover this portion in case of dynamic proton NMR. Okay. See this one. The H1 and H2, these two are diastereotropic in nature. If you consider the substitution criteria, H1 is replaced with Y, you will get the trio compound. H1 is replaced with, here you can say this is H2. H2 is replaced with Y, you will get the erythro compound. So erythro and trio isomers are different. That's why H1 and H2 are different. So similarly, you can identify different kinds of sets of protons in these molecules. Okay. These are some of the examples in case of the non-Bornean systems. Generally, this identification is very important in case of the CSIR net examination. The people will ask you in the examination, there you will get the structure. In the structure, you need to identify different kinds of non-chemical equivalent set of protons. Chemically equivalent and chemically non-equivalent sets of protons. In case of annulines, all internal protons are considered as one set and all external protons, here we are observing protons, right? All external protons are considered as one set. In all the cases we are observing hydrogens. You can write hydrogen in all the cases. So all internal considered as one set and all external considered as one set in this case also. So these are the some of the examples which are related to the chemical equivalency and chemical non-equivalency sets of protons. So with this we will end this topic. So in the next lecture we will have a brief discussion on principle of NMR spectroscopy. In the principle we are having two techniques. First one is the quantum approach, second one is the classical approach. Okay, thank you very much.